copper wire is everywhere, powering homes, charging phones, enabling data transmission, running through cars, appliances, factories, and the global electrical grid. But behind every strand of copper wire is an enormous industrial process built on molten metal, oxygen-free casting, continuous rolling mills, multi-stage drawing towers, annealing furnaces, precision dies, high-speed capstans, and automated spooling systems that turn a heavy cast rod into hair-thin wire moving faster than a sprinter. Today on the How Factory, we're going inside the massive facilities where copper is melted, purified, cast, stretched, annealed, coated, and wound into perfectly uniform spools. What begins as raw mineral pulled from the earth becomes an engineered conductor that must meet exacting standards for flexibility, conductivity, and strength. And the transformation is nothing short of industrial magic. The journey starts at copper smelters, where refined copper cathodes, often 99.99% pure, are stacked like heavy metal plates. These cathodes arrive at wire rod plants where they're melted down in enormous electric furnaces. The copper is heated above 1,085 degrees Celsius until it becomes a glowing orange-red liquid. To ensure maximum conductivity, the melt must contain almost no oxygen, sulfur, or impurities. Oxygen contamination can make copper brittle, so the molten metal undergoes a refining step where inert gases like nitrogen or argon bubble through the melt, stripping out dissolved oxygen. Chemical additives bind with impurities, which rise to the surface as slag. Every batch is tested with spectrometers to verify composition. Only when purity reaches near perfection does the molten copper move into the casting line. Most modern plants use a continuous casting and rolling process to transform molten copper directly into long rods. In this system, molten copper flows through ceramic tundishes into a rotating steel wheel or mold. As the copper cools, it solidifies into a thick bar or cast bar, roughly several centimeters in diameter. Water sprays cool the bar as it moves, and as soon as it exits the mold, massive rolling mills grip it and begin reducing its thickness. These rolling stands, arranged in a long row, use hardened steel rollers to compress the copper bar again and again, flattening and elongating it into a continuous rod. Sensors precisely measure temperature, thickness, and alignment. If the rod becomes too hot, water sprays activate. Too cool, and heating elements adjust the temperature. By the end of the rolling line, the bar has become a smooth, flexible copper rod, about 8 millimeters thick, the standard feedstock for wire drawing plants. This copper rod is wound into giant coils weighing tons. Once cooled, the coils are transported to the wire drawing area, where the transformation from rod to wire truly begins. The rod is fed into a drawing machine, a towering system consisting of hardened tungsten carbide or diamond dies arranged in a sequence. Each die has a slightly smaller hole than the previous one. As the copper rod is pulled through the first die, enormous tension forces squeeze and elongate it, reducing its diameter. The newly thinned wire then moves immediately to the next die and the next, undergoing successive reductions. A typical wire may pass through 10, 20, or even 30 dies, depending on the final diameter. The process is continuous and extremely fast. By the final stage, the wire may be moving at 30 meters per second or more. Because drawing wire creates heat from friction and deformation, cooling is critical. Lubricants, often specialized oils or emulsions, flood the dies to carry away heat and reduce wear. These lubricants must stay perfectly clean, so the system constantly filters them with centrifugal separators and fine mesh filters. Even microscopic particles could scratch the wire or damage a die. Workers monitor the lubricants like a lifeline because a broken die or overheated wire can snap the entire line, creating hours of downtime. High-speed cameras and laser micrometers continuously measure wire diameter, detecting deviations as small as a few microns. If the wire begins drifting outside tolerance, automated controls adjust tension or speed instantly. As copper becomes thinner, it hardens, a side effect of the cold working process. Hard wire is brittle and unsuitable for electrical use, so the wire undergoes annealing, a heat treatment process that softens the copper while preserving its shape. Inline annealers use electrical current passed directly through the moving wire. As the current flows, the wire heats rapidly to several hundred degrees Celsius. Water sprays cool it immediately afterward, freezing the copper's crystal structure in a softened state. This makes the wire flexible, bendable, and ready for spooling or further processing. Because the annealing occurs while the wire is moving at high speed, controlling temperature is incredibly precise. Too low, and the wire remains hard. Too high, and it oxidizes or weakens. Next, the wire may pass through a cleaning station to remove residual lubricants. Depending on the plant, cleaning can involve steam jets, alkaline baths, ultrasonic agitation, or high-pressure rinsing. Clean, annealed wire then moves toward the coating or bunching stage. Some wires receive a coating of tin or other metals, improving corrosion resistance and solderability. Tin plating lines use molten tin baths or electroplating tanks, where electrical current deposits a thin, even layer of metal onto the copper surface. The coated wire is then dried and polished before being wound. For multi-strand wires, like those used in flexible cords, individual copper strands are grouped in bunchers or stranders. These machines spin multiple wires together under controlled tension, creating bundles that combine flexibility with conductivity. Planetary stranders, tubular stranders, and rigid stranders each produce different constructions depending on application. Some wires receive insulation at this stage, extruded through high-speed plastic molding machines. But pure bare copper still represents a massive portion of global production, and its journey ends at the spooling lines. Spooling is far more complex than it appears. The wire, now hair-thin and moving at extreme speed, must be wound onto spools with perfect tension and alignment. Automatic spoolers guide the wire back and forth in precise patterns so it layers evenly without tangling or collapsing. Tension sensors prevent slack or overpull. When a spool reaches its target weight or length, the machine automatically cuts the wire, seals the end, and begins winding on a new spool without stopping production. These systems must synchronize perfectly with the drawing and annealing operations upstream. A moment of slack, a faulty cut, or a misaligned spool can cause wire breakage that halts the entire line. Finished spools undergo inspection. Technicians measure conductivity, tensile strength, elongation, diameter uniformity, and surface quality. Any spool that deviates from strict specifications is rejected or reprocessed. Because copper wire is a critical component in electrical systems, quality standards are exceptionally high. High-voltage transmission wire, motor windings, telecommunications cables, and building wiring all require different mechanical and electrical profiles. Data from each spool, from casting to final winding, is logged for traceability. After inspection, spools move to packaging. Large industrial spools may be packed in wooden crates, wrapped in protective plastic, or mounted on metal drums. Smaller consumer spools go through automated wrapping machines that apply shrink film, labels, barcodes, and palletization. Palletizing robots stack spools in predetermined patterns to maximize stability during transport. Trucks and cargo containers carry copper wire across continents to manufacturers who will transform it into magnets, transformers, motors, circuit boards, and power cables. Behind the scenes, copper wire production demands constant monitoring and precise automation. Computer systems track die wear, lubrication purity, rod temperature, annealing current, and wire tension. Predictive maintenance sensors listen for vibration changes, bearing wear, or abnormal temperature patterns in the drawing machine's capstans and motors. Surface scanners detect pinholes, oxidation spots, or imperfections invisible to the human eye. Advanced manufacturing plants integrate AI-driven controls that self-adjust rolling pressure, drawing force, and annealing curves to maintain perfect consistency. What makes copper wire manufacturing extraordinary is how the process compresses heavy metallurgy and fine micromechanical precision into one continuous high-speed system. Molten copper becomes a solid rod, The rod becomes a drawn thread. The thread becomes a conductor measured in microns, all under the coordinated control of temperature, tension, lubrication, electricity, and speed. Every strand of wire represents metallurgy, physics, automation, and craftsmanship working in perfect synchrony. And that is exactly how copper wire is melted, cast, rolled, drawn through microscopic dies, annealed, cleaned, spooled, packaged, and shipped worldwide. A breathtaking combination of heavy engineering and high-speed precision shaping one of the most important materials in modern technology. Thanks for watching The How Factory, where we reveal how the world really works. Don't forget to like, subscribe, and join us again for more deep dives into the machines and systems behind everyday products.